Hi, hello, all to good morning to all. And today the topic is we are going to see about column. Column. And what is a column actually? It's defined as a vertical load bearing member supporting the axial compressive load chiefly, and the structural member used to transmit the load to the structure on the foundation. This all we know. This is the basic, and we can see the picture here. So this is a type of a column which is in practically what we're seeing. The bending action in the column may produce a tensile force over a part of cross section still. The column are called a compression member because the compressive forces dominated their behavior. So let us call it as a column or a compression member in field, and that will dominate the behavior of the forces. And these are all some of the cross section of the column we may see here. And this is a column and the reinforcement detailing. And this is a cross section of the column and longitudinal section of steel. And sometimes we may use a spiral in circular column. So you may see the reinforcement in the spiral. So here we have two type of reinforcement. One is in a normal lateral reinforcement, longitudinal steel bars and traversing steel bars, and the spiral type. So here we may identify the switch. So usually for the circular, we use the spiral kind of an reinforcement of longitudinal traversing bars, or which may call it as a spiral, or we may use as a rings also. We are using the longitudinal reinforcement. So, what is the use of this longitudinal reinforcement? To assist the concrete in resisting compression, so as to reduce the overall size of the column, to resist any tension that might be developed due to the bending caused by the traversed load, eccentric load, or the momentum. So, and to reduce the effect of creep and shrinkage due to sustained load. To prevent or delay the sudden brittle collapse also, the longitudinal reinforcement is used to impart the necessary ductility to the column. And the next, the traversing reinforcement. You may see this traversing reinforcement. That is, we call it as a ties. To prevent the buckling of the longitudinal bars, to prevent the longitudinal splitting of concrete, to conflict the concrete, to resist the diagonal tension due to traversing shear, to hold the longitudinal reinforcement bar in the position, to prevent or delay the sudden collapse impacts the necessary ductility of the member. So these are all the things for which we are using this longitudinal reinforcement and also the traversing reinforcement. So right. So as we know that column is a compression member. So based on which the effective length of the compression member has been given by the condition is given by the four conditions, as well as far as we have many conditions and as per ISO 6 code, and we are seeing some of the usual condition we use, which is both ends are pinned, the column both ends are pinned. That is effective length is L is equal to L, and if it is both ends are being fixed, the effective length will be 0.5 times of L. And one is fixed and one is pinned, which is zero point 0.7 times of L. One is fixed and another is free, which is effective length is 2L. We are using this as an effective column. The effective column recommended by the IS 6 code, which is in page number 4, we can visit the code and we can see that the various effective length of the compression member in page number 94 in IS 456. Right, slenderness ratio. So how long thin is something basically the ratio between the length of the width, length to its width. That is effective length to the lateral dimension, which is nothing but of a simple architect definition for a slenderness ratio. Simplest engineer definition, which is L effective by R. So R we know that which is in a radius of gyration. So buckling and bending axial are applied. So this is in a centralness ratio, which is L effective by R. R is nothing but a root of I by A, that is amount of inertia by area. Right. The column depends upon the ratio. When the lambda value is greater than 3, which is in a pedestal compression, when the lambda value is less than, for example, the lambda value is if the less than 3 or less than 12, and less than that is not a lambda actually, that is a slenderness ratio. Sorry, the slenderness ratio is I mean, less than 12, if 12 less than or lambda is greater less than 60, which is known as an buckling failure column, and crushing failure column, which is if 3 less than lambda or less than 12, which is in a crushing failure occurs. So if 60 is less than that is slenderness ratio is not considered as in a column. So let me have you have two type of column here. One is in a short column and a long column. So short column, you know that the effective length by the least lateral dimensions which should be less than 12, which should be less greater than 12, which is in a long column. So short column fails by buckling alone. Not only buckling, it fails basically in buckling, and it is fails. And the short column basically fails in crushing. The slenderness ratio is less than 45, and the slenderness ratio is greater than 45. Subjected to compressive strength and subjected to buckling stress. And the short column, radius of gyration is more, and in the long column, the radius of gyration is less. Load carrying capacity is more for a long column ends because it has a crushing type of the thing, and we can take some as it is in a compression member, we can take a maximum of loads, and load carrying capacity is less in the longer column, so we prefer always a short column in the structure, right? So type of loading we have. So we have three type of loading in a column, which is an axially loaded column, uniaxially loaded column, and biaxially loaded column. So in axially loaded column, we may able to see that the load is actually acting in the center part of this view. You can see this view, and we have which has a center part of this column, which is a load will be acting. And here, in the uniaxial, which may have some x-axis, some distance, and laterally the load will get off acted. And here in the biaxial, from the x and y direction, the point has been marked in the green, and that may have some two direction of moment with a load. Here, one direction of moment with a load, and there will be no moment, only the axially loaded will be acting. So load acting on centroid of the column, axial load column only. So load acting in the eccentric of x and y axis, load and mx, that is moment. The axial load of mx and my, that is moment of mx x direction and y direction, which deals with the biaxial kind of column. So subjected to load acting along longitudinal axis, subjected do not act on the longitudinal axis of the column, load in eccentric to x and y, and the eccentric with respect to both axes is called a biaxial. So these are the three kind of a column depends on the loading. So we may have these are all the column size, right? So we can identify. You may have three kind of column. That is, one is plugged in red, and one another one is plugged in blue. We may able to, and another one is in similarity. So let me have. We can identify this is a plan of a structure. Let us identify that B2 and C2 will belongs to an axially loaded, and B3 and uh, C3 will be C3 that is surrounded by blue. Around us is nothing but of uniaxial, and other than the column is a biaxial. So you can see here there is no any possible of moment in B2 and C2. So it is an axially loaded. There is no any moment. And B3 and C3 we may see that the two connection is there for this, and one end is free. So in one end we may have some load. I mean that is one end we can have a moment. So that is we call it as uniaxial. And biaxial is two end is connected, but two end is free actually. This side and that side. You can see the D3, D1, and A1. So that is the column positioning is of biaxial column. So if you are having some key plan with you of column, you may able to identify the column. Right. So these are some of the design column requirements for a column. So longitudinal reinforcement of main bar as per class 26.5.3.1. The percentage of minimum steel should be of 0.6 to 6 percentage of cross section. The maximum bars are 4 rod of square column, 6 bars for a rectangular column. And pitch as per class 26.5.3.2 as per IS 456. The least lateral dimension of the column are 16 times of the dia, and the smallest longitudinal bar are 300 mm. We can take it as or 0.25 diameter of the largest bar. So these are all the traversing reinforcement and the longitudinal reinforcement that has to be provided for in a column as per IS 456. So let me know this is the compression member. So these are some of the design assumptions let me have as per IS 456. Right. So as we have seen some percentage not to exceed of the reinforcement and for the ties and the unsupported length. So like this, we have some design assumptions and based on IS 456. And as we know, which I should have a minimum eccentricity of 20, and this is the eccentricity formula. And as we know, we have seen some eccentric distance here. So that eccentric distance can be identified based on this formula. So this is an design of an axial column. First, we can find the effective length based on which first you have seen the different kind of electrical length of a column. Page number 94 and table 28, slenderness ratio and eccentricity, and the reinforcement page number 71. You can identify based on this formula. You can identify the reinforcement, and based on the page number 71, we can sorry 49. We may identify the pitch and diameter of the reinforcement. If in case of an helical, from the page number 71, the volume of helical by volume of core, using this formula and the pitch conditions which has been given in the class, we can identify the reinforcement. So these are the few steps that is to be followed in the reinforcement of a column. And that's all for the video. And thank you one and all for being in touch with this video and watching. Thanks for watching all. And thank you.